Morning, everyone. I'm Sandra Esteves. I'm a professor of bioprocess technology at the University of South Wales, and I'll be presenting, hopefully. Okay, turning waste into resources. So we work a lot with microbes, and I'll give you a flavor of what types of waste we are interested in, and you'll be surprised of what we get excited about. So just a quick introduction for the ones that don't know our work. We started looking at anaerobic digestion since the 1970s, and we've gained interests as part of that. So this was like the heart of our activity. So we do wastewater treatment, bioenergy production, biohydrogen production, bioelectricity, metal recovery, carbon conversions, gas conversions, and we also look at things like life cycle analysis and economic evaluations of all these processes and products that we work with. Just a very quick slide here just to show you some of the lab facilities that we've got. So we've got digesters and fermenters at very, very small scale and larger ones, and we also have the pleasure of working at full scale with collaborators. So we've got a lot of analytical equipment around the bioprocesses that we're developing. Again, just some slides again on photos about the type of reactors that we work with in the lab, and these will be full of microbes that have got a function to deliver. In this case, we work with C1 gases, so these are gases like carbon monoxide, carbon dioxide, and methane, two products. We've got a vision that microbes actually sit in the center of a good, sustainable integration between sectors. Biotech can help us deliver sustainability, and these are just areas where we see that we can work towards. So within nutrient and metal recovery, within CO2 recovery and conversions, within delivery energy systems as well. For example, energy storage as well. So we could use pick up on power that is generated by solar or by wind or marine means, and we can actually convert it to other ways of storing energy instead of power, for example, in a gas form, for example, or into a polymer or protein production. So there's all sorts of nice interactions that we can do with microbes. And this is areas that we see working, so CO2 and ammonia recovery. I don't know if you're aware, but power grid constraints are still around in the UK and many other countries, by which you can even install facilities for production of electricity, but you can't really connect them to the grid. So there is wasted opportunities there, and this is in the south, and all those little red dots actually means restricted networks. So we're looking at energy storage. If we're going to move from fossil fuel to renewables, 100% or close to that, we need to be able to store energy as it's being produced, because it's more irregular than just using a fossil fuel. Decarbonizing fuels and decarbonizing gases, that's also what we are working on. Recycling and production of plastics and bioplastics. That's another area. Metal recovery, resource recovery. On the right-hand side there, actually, I'm not sure. Oh, I don't think I've got a pointer. That is actually frass. That's insect waste. So we're very interested in everything. So if anyone fancies having an insect farm at the back of their garden, we'll be interested in that too. So we deal with wastewaters, animal wastes, biomass, residues, etc., etc. And we're very, very interested in production of alternative protein sources as well. So with our microbes, we can actually grow them to become the future protein for animal feed and also for human feed as well. And obviously fertilizer. So as you can see, microbes can have a role in all these functions. So biotech is a very exciting area to be working in, I think. So just for the ones that are not familiar, anaerobic digestion, the start of our innovation work, is actually at full scale, is a commercial technology now. And all these little dots means a plant. These plants can have, 20,000, 30,000 tons of material coming into them, and they can be, half a megawatt, 1 megawatt, 2 megawatts worth of electricity, but also connecting to the gas grid, for example, or fueling vehicles as well. So a number of them that deal with sewage, okay, the water industry plants, and municipal on your food waste side. I don't know if you realize that some of your food wastes, and especially in Wales, end up going to these type of facilities. If we look at the contribution that these facilities are making just from an energy point of view, not even from a waste reduction and mitigation point of view, we've got things like the ability of converting to about 12% of domestic gas demand currently. And we could have 30-odd% possibility if we do a little bit more work, and this was a scenario by 2025. Okay, so the potential is there. There needs to be work, and if you look at Europe, has put really high targets for gas. Obviously, the Ukraine scenario has driven the most interest as well, but you can see a lot of the northern countries are really focusing on replacing the Russian gas with a lot of the gas that we can be producing locally. Is there a game already? So we've got a project is funded by effectively the water regulator, Water Breakthrough Challenge, and is transforming the energy balance of wastewater treatment. So we all produce sewage, I'm afraid, from our homes. And in the past, we used to have, well, in the past and present really, we used to have the wastewater is treated via two modes, an aerobic process and anaerobic process. What's the data that has been gathered so far is that actually people were worried with methane that could have some emission losses. What is worrying is actually nitrous oxide as well. This is a gas that has over 300 times the potency of CO2. And if you actually aerate, but you don't aerate enough, which typically happens, you end up producing these type of compounds as well. So we are moving completely out of the aerobic way of treating wastewaters to a fully anaerobic way with a number of water companies, with a huge savings in terms of carbon, etc. I just wanted to introduce this concept. So power can be produced, and as I mentioned before, lost if it's not been utilized. We got funded via the BASE project and looking at how can we actually raise the TRL, the technology development, on converting, say, hydrogen that comes from electrolysis, for example, with CO2 that comes from all sorts of industrial processes, and actually produce other gases. It could be methane, propane, butane, ethane, but also carboxylic acid, etc., etc. So this is a project that has been completed, and we're looking forward to some further development and commercialization of technology. The same technology is actually being worked on in another project, and just really to give you a flavor of what type of companies are engaging in these type of developments, from wastewater to engineering to heat recovery to AD plants. They have quite a lot of CO2 in their gas as well. So it's interesting to see that, you know, we can actually merge a number of sectors with similar interests as well. So this is a technology where we could potentially produce a methane, but it can be other molecules as well, depending on what we do with the microbes inside that reactor there. And that's how these things look. For example, this project looked at carboxylic acids. What are these things? So acetic acid, butyric acid, propionic acid. They have huge applications into a number of areas, from resins to paints, etc., etc. And they all go to people's homes again, you know? So it's a bit like a loop between, you know, what can we get out of food waste, what can we get out of sewage that can actually feed our daily needs. from a number of applications, okay? Other area is around flexible methane production. I don't know if you were aware. If there's always peaks of utilization, a bit like peaks in delivering people to the train station. So in the morning you need your baths, you're using more gas, and then people go to work, and then in the evening for cooking, etc., you need more gas again. So that balancing of the gas grid is very, very required. But how can we do that, say, from a production of an anaerobic digestion plant, which typically is tends to be a flat output there? So we're looking at, say, recovering through carboxylic acids, which are intermediates within the process, so that we can then be able to produce the gas when is required and not store it in the form of gas, but in the form of liquid. We see these very useful not just from a daily fluctuation, but also from a seasonal fluctuation. A summer's evening requirement for gas is much lower than Christmas Day, for example, okay? So that's where we see quite a lot of these demand and supply being delivered by processes. We work in other areas, so not just methane, propane, butane, ethane, as other fuels as well. And an area that we've started for some time, but we continue, is things like acetic acid. Acetic acid is one of the largest chemical that's been used. It's the 34th highest production volume chemical in the world, and we can actually produce that. Typically, in the chemical industry, you start with methane and you end up in acetic acid. Well, our processes produce acetic acid and then methane afterwards. So we can start recovering these chemicals, and then, produce your polymers, produce your paints, etc., etc. How can we produce these? We can produce it from all sorts of things. So food waste from home, and that's the left-hand side there. We can actually produce quite dense materials within volatile fatty acid. And we can start recovering those. On the right-hand side is, for example, an application for animal slurry. How can then we take out these acids and store them so that we can use it for applications like food production, like energy production, whatever. Same here, we can pick up on hydrogen and CO2 as well, and we can start concentrating those as well. So there's a number of opportunities there. Same with urea. People talking about the cost of fertilizer production, the environmental impact of fertilizer production. You could start in methane as well, okay? Methane is a molecule that has not been used just for energy applications, but as you can see, for a number of the chemical applications as well. It ended up in things like ammonia. Well, we've got lots of ammonia in sewage and food waste. We need to recover that. Same with phosphate, okay? So these are areas that we're very, very interested in. I don't know if people realize, but there is a major stop in terms of planning because of what we've got in our environment, in Wales and the South Wales particularly. And there's a phosphate excess in our rivers, in our soils. And that's stopping a few £1 billion worth of investment in new builds, for example. Yeah? So we can recover that from a centralized perspective within wastewater treatment facilities, but even in rural applications, we can do that on house-to-house basis as well, or community base as well. So in reality, this shouldn't be a stop for new houses. There may be other reasons for that, but phosphate and nitrogen recovery should not be one. We're also very interested in carbon, and carbon, say, from boilers, etc. We see, local authority picking up our wastes, solid waste from home. Our sewer goes into a little pipe and disappears, and people are happy with that. Can we collect CO2 from our boilers? Can we actually collect our nutrients directly from our homes? So we can start thinking about other models that maybe are not in existence now. We've been working on digestate. Digestate is the product after digestion, so it's very rich in nutrients, okay? And some graphs there, ammonia and phosphate. And we can actually strip more than 90% of these compounds and have that in a very concentrated form that they can travel then, is quite efficient for them to travel wherever they require to be used, okay? So again, that's not an excuse not to do things, I think. Same with if we actually have a rural type of dwelling, and it can't be built because there will be no, there's excess of phosphate, we can actually take phosphate right down at the site with a simple resin that can actually be regenerated as well. So these opportunities are arising, and they can be delivered very quickly. Same with CO2. Can we actually strip CO2 from people's homes, from boilers? That's very possible to do as well, and very high efficiency as well. So other opportunities into play. Just to finish off, polymers. So we've been very interested in how bacteria produce their own polymers. Humans store energy in terms of fats, okay? Some people do it very efficiently as well, right? But microbes do it as well in the form of things like those little granules there. And these are effectively very interesting polymers that we use in a number of applications. There's over 150 types of polymers that different bacteria with different feedstocks and slightly different run processes can produce, from rubbery to more stiff polymers, etc., etc. And we can make a number of products. We've been working some within the medical world, so things like stitches, capsule enclosures, but also fake skin, artificial skin, scaffolds that put inside our body. So it's a very bio-relatable polymer as well. And microbes can access it anaerobically and aerobic as well. So can we start using these polymers to replace a number of fossil fuel-derived polymers? And in these cases, actually, can we make, sorry, I can see the format is a bit lost there, but can we make these polymers out of sewage instead of driving it to a methane molecule? Can we actually recover it and produce it there? Can we produce protein, polymer, and a fertilizer at the same time? These things are possible, okay? They've been demonstrated in small scale. Let's make it at larger scale and move on. Can we degrade this polymer? Yes, of course. If you start doing interesting mixes with other polymers that are less degradable, with other blends and chemicals, that will reduce. But we can do that, and actually we could have it as the caddy liners that currently do not anaerobically degrade and actually have difficulties in degrading aerobically as well, for collection of food waste, for example. So that's an opportunity there that we want to move forward. Very interesting microbes. We've got microbes that work with light, for example, that can convert nitrogen to ammonia. They can take CO2 as a feedstock and produce things like spider silk equivalent. So very tough polymers that they can deliver from that perspective. One project that we involved with is with Tata, and these are buildings that are slightly different from your brick building. These are steel, galvanized steel with lots of foam around them, and we're trying to de-zinc, and this de-zinking with products that microbes have produced, and this is being done very effectively, and we're moving forward in scaling up this technology. The foam that is within that is a very tough foam. If it's combusted, produces very nasty chemicals, okay? And we're trying to use microbes in order to do that. The left-hand side is the polymer without a microbe. The right-hand side is with the microbe. So you can see the microbe is starting to attack that polymer. Very interested in products such as hydrogen, CO2 from this foam. Toothbrushes, we're also very interested in toothbrushes, okay? And we're helping develop bio-based brushes as well. We're looking at microbes, what reside in these brushes after utilization, etc. Very interested in films and production of biofilms from a number of sources. And we're also working with the NHS, a couple of NHS, Tom and Joanna around, looking at the boots, okay? Everyone will have one in their cupboard somewhere, right? Orthopedic boots. Apparently every year is 22,000 a year being dashed out, right? So what to do with these things? Can we produce the foam inside from a biopolymer? Can we actually reuse, clean and reuse, etc.? So we're looking at opportunities around that. I just wanted to tell you about 2 projects, Beacon Project, biomass to endless products, from pharmaceuticals, nutraceuticals to resins, etc. If you want to talk to us, we're very keen to work with you under this Beacon project, and the biopolymer project as well there, that we're very interested to talk to people, biopolyesters and polyamides. I don't do this work on my own at all, and there's a lot of people that I would like to acknowledge in the team, and also supporters and funders as well. Thank you for your time.